Okay, here's my little experiment. I wanted to try out from the pictures posted with this video in the thread. You'll be able to see exactly what I've done, but for those that aren't going to see the thread, just the video, I'll try and explain. The core, our Toroid core is made from liquid steel. The way I did this was to take one of the kiddies plastic donuts, cut it in half. I then formed the one half of the core and the other half of the core with liquid steel, let it dry, pulled those two halves out, sanded them all up so they're nice and flat and even. Now before I glued the two halves together, I wound one secondary around one half of the core. So the wires of the windings will be going through the centre of the complete core. So we're going to call that secondary blue, or secondary B, because we're going to have channel B of the scope placed across that coil. So once the coil was wound on the one half, I then once again mixed up some liquid steel and I glued the two halves together, like so. Once they were dry, I then wound on the primary and the other secondary with the primary around the whole core. All three wires were cut to equal lengths, so that means that on primary and secondary 2 we will have more turns, and secondary 1 will have less turns because it's around the whole core and not half the core like secondary 2. So the one that's wrapped around half the core is our blue channel on our scope, and the one that is wound on the whole core with the primary is the yellow channel on our scope. The primary coil is going through our amp meter, the signal is coming from our signal generator. It is not amplified, it is straight out of the SG into the primary coil. Turn our scope back on. Okay, so our amp gauge or our meter is reading 0 amps as set on AC. We are using AC, however the frequency at the moment is about 156 kilohertz. The scope says 155.998 kilohertz. The signal generator says 156. So extremely close. Amplitude is 14 volts peak to peak, and of course it is an AC wave. Okay. Before we go any further, the two secondaries, secondary A and secondary B, have a 100 ohm resistor across them as they load. And like I said, at this frequency I don't think this meter will be telling us too much at all, so we'll pay no attention to that because it's bound to be incorrect. So as you can see, the blue channel, which is the secondary that's wrapped around half of the core, is slightly lower in amplitude than the secondary that is wrapped around the whole core right alongside the primary. Channel 1, which is our yellow trace, 840 millivolts RMS, and channel 2, which is our blue trace, is 560 millivolts RMS. So we can see at the moment that the secondary that's wrapped around the whole core with the primary is giving us more current output or power output than the secondary that's wrapped around half of the core. But it gets interesting when we start to lift the frequency up, and we're going to go up quite high. So we'll start to lift it up. You'll be able to follow the frequency on the scope, and I'll just adjust our time divisions a bit. You can see the amplitude of both start to climb. Okay, so I'll take it up to around about 1 megahertz. So at 1 megahertz at the moment, and as you can see, not too much has changed, but you can see we're starting to get a slight phase drift on our secondary, which is well, it's actually between the two secondary coils. The phase is starting to shift between the two, even though they are basically wound together. The only difference being, of course, is that our blue channel, or secondary 2, is the one that's halfway, wrapped around half of the core. So we'll keep climbing in frequency. Go up a little quicker than that. So now you can see that the phase shift between the two secondaries is starting to move out of phase quite a bit. I should mention we are on 1 volt divisions and 50 nanoseconds on our time divisions at the moment. But not much happening in the way of the amplitude between the two. So we still have a lower amplitude or lower power output from the secondary that is going around half of the core. So we'll keep on lifting the frequency up, and now we can start to see a change happening. And it's right about there. Okay. Now we can see that our two secondaries are nearly close to 90 degrees out of phase from each other. And we can see channel 1 is 1.56 volts RMS and channel 2 is 1.44 volts RMS. So we'll play around with the frequency a little more. And you can see right there we start to go way out. Okay, so that's about as good as we get. So now we have a case where the primary or the secondary, both secondaries, are putting out pretty much well the same current, and they're about 90 degrees out of phase from each other. So I find that quite interesting. get a phase shift between the two secondaries on the same core running at the same frequency, and of course the difference being one is wrapped around half of the core and the other is wrapped around the whole core. So I'll keep on playing around with it a little bit longer and see if we can find anything else out about it, any other magic tricks it might have to show. So, but that's my little test, and that's what we have so far. Cheers guys. Okay, I'm just going to tack this on the end. I've lifted the frequency right up. I'm just playing around with this setup. Now 11.93 megahertz. Now I'll just explain what I did before. I haven't changed the setup at all, but I have one of the scope probes hooked up in opposite polarity to the other, as you would have seen in the first part of this video. I haven't changed that, and the reason I did that was to separate the two waveforms on the scope so we could clearly see what was going on between the two coils. But at this frequency here they are now lined up, which means that the phases are 180 degrees out from each other, and channel 2 is now putting out more power than channel 1, which means the coil that's wrapped around half the core across that 100 ohm load is now putting out more power than the coil wrapped around the whole core with the 100 ohm load. The other interesting thing, and I'm not going to pay much attention to this, but the current draw has gone negative as far as our meter is concerned, but at this frequency I don't think there's any way in hell that's going to be reading an accurate power input or current input to the device. But we've managed to throw the phases out of the two secondaries 180 degrees at 11.93, and just to show you that, I will wind the frequency back down again and we can watch what happens. Right, and I'll let you have a bit of a look at the whole picture as we're going. And there you can see, oh, there was a bit of a hiccup there, right there. 2.9 to 3 megahertz is a pretty big jump. I'll just drop the voltage divisions down. And time divisions. So now you can see that the phases are lining up again, but I just thought that was very interesting. Oop. There you go. So right on 11.7 we can throw the phase out 180 degrees and we can have a slightly higher output of power from the coil that's wrapped around half of the toroid than that of the coil that is wrapped around the whole toroid. So interesting stuff. Keep on playing around with it a little bit, but it's quite cool how we can get both secondaries to go out of phase like that. Yes, like I said, we won't pay much attention to that. We'll have to perhaps hook a resistor across the input, throw the scope on that and have a look through the scope. That's what I'll do next, but that's what we have at the moment. So all in all, we really have, we've got 100 ohm there, 100 ohm there, so 50 ohm load across the output of the transformer, if you want to call it that. At the moment we only have 280 millivolts RMS across both of our secondary coils. Alright, thanks for watching guys, cheers, and we'll keep you up to date.